Hello, everyone. Welcome to another ACE Spotlight event. If you would like to hear more about this type of technical talks, you can go to our website, ai.science, and sign up there or follow our YouTube channel. Today, I'm thrilled to have Evan Oldridge. He's a senior manager in the RecSys platform team at NVIDIA. He's leading a team of engineers and data scientists building tools to accelerate recommender systems on GPUs. I also have Omar Nada. He is the ACE stream owner for recommender systems. He's a senior data scientist at RBC, specializing in recommender engines. He's also the research lead and stream owner of recommender systems at ACE. Gentlemen, glad to have you guys here. Without further ado, Evan, please take us away.
Thanks so much. I'm excited to share with the group. This is one of the sort of the passion projects I've been working on for a number of years. We were talking about it a little earlier. The recommender system space is a very interesting but very challenging space to deploy models into production with, and in particular, GPUs can be a very challenging thing to use. And so what we're working on at NVIDIA is building tools that allow companies to develop recommender systems end to end on the GPU. And I'll walk through some of the phases here. So I appreciate the opportunity to share some of the work that my team's been doing. There's a large number of us working on this now. A year or two ago, it was just me. So it's exciting to see how much this has grown, and we're very excited at NVIDIA to really kind of push recommenders. It feels like the next big thing that we're working on here. So it's very exciting to see the improvements that we've got. I'm excited to share some of the results with you. So at a high level, what we're trying to solve are some of the major challenges that we've seen, and that I've personally experienced, and that my team members have experienced, and that I'm guessing that you've experienced if you're building recommender systems in production. And these fall into sort of four broad categories here, and I'll talk about how we address those in the tooling. But feature engineering tends to be one of the more interesting challenges in recommender systems. I think, if you're working as a data scientist, the creation of a data set is one of the biggest problems that you're going to face. The modeling actually becomes the easy part of the problem after you get to that point. And building those features can be, hundreds or even thousands of iterations over the data set in sort of an ETL fashion to try and pull the data, iterating over it and trying different combinations. And that's, that can take way longer than the training. And so this is something that we've worked with a team called the Rapids team at NVIDIA, and they developed a data frame style on GPU engine, and we've kind of adapted and built an abstraction on top of that to make it easy for recommender systems. Data loading is the next section that you'll run into, and when you're training recommenders on GPU, if you think about when data loaders were built, it was in the major frameworks like PyTorch and TensorFlow. They were built back in the day when what you were loading was images, right? So if you take those images and think about sort of the amount of data they contain, there's these sort of very large chunks of data that are probably being manipulated a little bit for augmentation and then aggregated into a batch on the CPU and passed across to the GPU. But for a recommender system, the data that you have is usually a single interaction for a user. It's a column in a data frame, and so that column in the data frame, that single interaction is, if you're trying to aggregate a bunch of those, you're essentially grabbing kind of random access into either memory or the worst case disk, and so it doesn't make sense to be accessing the data in that way. And so we built some tooling and methodologies to be able to basically access the data in a way that's much more efficient to pull it into GPU memory. One of the big challenges if you sort of are dealing with a recommender system of scale is that the embedding tables that you're using to represent your categorical variables don't really fit on the GPU when you start to hit millions or tens of millions or hundreds of millions of users or items. And so and in particular when you have both of those, you struggle to fit the embedding tables on the GPU. And so when you can keep all the embedding tables and everything in GPU memory, things are much faster to train. And so we have a tool that we've developed to help scale the embedding tables onto the GPU. And then finally, the challenge of production deployment is a non-trivial one, and I think one of the things that we've been thinking about a lot is ease of use and production deployment, and how the feature engineering steps that have been done need to be applied at inference time, and how sort of the model components need to flow through this system in order to be able to really build something that scales end to end easily. And so we built 3 core tools: NVTabular, which handles the feature engineering and data loading components; HUGECTR, which is our recommender specific training framework; and then Triton Inference Server, which is our sort of on GPU inference. And I'll talk about each of these in turn. NVTabular, the core idea is to really prepare massive data sets in minutes, and I'll give an example where we're blasting through a terabyte scale data set in minutes, literally. And then on the data loading side, we integrate directly with HUGECTR, which is sort of our training framework that we're aligned with. But we also provide, on the NVTabular side, data loaders that allow you to sync with PyTorch and TensorFlow, and we're building sort of this common backend. All of the NVTabular tooling is built upon the amazing work done by the Rapids team and the Rapids framework. And so we're using this technology called Dask-QDF, which is essentially leveraging the power of Dask, which allows you to scale out to multiple GPUs and multiple nodes very easily. And even on a single node ends up being more efficient. And then on the, basically creates a task graph to appropriately schedule all of the things that need to be done. And what we do with the NVTabular side of things is we take common operations that you're going to do on the data science side when you're building this feature engineering, when you're building the training data set, and sort of automate those or make them very simple to write. So, as an example, instead of for normalization, instead of having to specify that you want to sort of compute the mean and compute the standard deviation and subtract and divide and then load that column back into the data frame as your new normalized variable, you can just say, these are my continuous variables, we're going to normalize them. So that's at a high level the Merlin recommendation framework. And what we're trying to do with this is basically provide something that is open source, that's easy to use, and that's GPU accelerated end to end. So you can do all of these steps on the GPU. And what we're seeing as customers begin to adopt this is with NVTabular, you're able to scale your data sets that you're processing up by a factor of 10x or more, because the processing of the data set is happening so much more quickly. And you can write the data set generation more quickly, and so you're able to explore more. On the training side of things, using our data loaders or using HUGECTR, you're able to accelerate the training. And so you're able to end up with better models end to end, faster iteration cycles, so your models are fresher. And what we're working on now is the inference components of how to integrate that directly into inference in a straightforward way. So I don't know if it seems like that may be a natural time to stop and see if there's any questions.
I guess so far we can move on. We can continue. I think the questions will come a lot from this point going on with the numbers you're going to share.
Perfect. Okay, sounds good. So NVTabular is our, and all of these components of Merlin are sort of designed to work together. NVTabular is we call it our ETL component. It's not necessarily a traditional ETL in the sense that we're not, you're pulling data from the data lake potentially, although we can point to data lake targets and cloud targets. But the idea is more of the iteration over the data set to do feature engineering and pre-processing. So it allows you to do kind of high speed on GPU pre-processing. It's designed to scale to data sets that exceed the GPU or even the CPU memory. And it does that using, like I said, Dask-QDF. So essentially what you're doing is wrapping the tasks into a task graph and then scheduling that, usually to minimize GPU or minimize the memory swaps and the memory loss. So, with this, there's a high-level API that allows you to focus on what you want to do with the data and not how. And the output of NVTabular can be consumed by PyTorch, by TensorFlow, by HUGECTR, and then also by a number of other kind of mechanisms. So the inputs can be files like Parquet files or CSV files or other formats. Parquet is our most optimal format. And then you can also input Dask task graphs, and so you can feed a QDF, Dask data frame. So you can feed a QDF data frame or Dask QDF data frame. The output of it is Dask QDF data frame, and so it's fully interoperable with the Rapids ecosystem. One of the things I want to highlight is just up on the right-hand side here, and we'll see the example in another format as well. I'm not going to talk about the scale of time, but this is in terms of the amount of time spent doing just a single run of ETL versus the amount of time spent training. And you can see, in the first two examples, these are sort of more traditional, like you're doing your ETL and NumPy and you're training on the CPU. And 75% of the time is taken doing the ETL. And similarly, for an optimized Spark job for the same task, you're optimizing. It's still, there's a reason why, and I think most data scientists will agree that like the adage 75% of your time or more, I've heard as much as 90% of your time is taken sort of optimizing and manipulating the data sets. And with NVTabular, we're able to reduce that quite significantly. So, you're able to shrink the amount of time you're spending doing the ETL runs, and to the point where the training is actually what's taking the most amount of time. So we're really excited by the Merlin ETL framework because it allows you to really scale out the data sets that you're working with, and it allows you to expand and explore new data sets that you would normally be able to work within a time frame that's sufficient for doing a reasonable training iteration. And it also allows you to iterate quickly when you're retraining your model online in production. At a high level, HUGECTR is sort of our training framework. So you can see, it's designed to scale from a single GPU to multi-GPU, depending on on your needs. There's sort of the major benefit here is scaling to multiple GPUs automatically, and there's a very elegant system that it uses behind the hood to do that, or under the hood to do that. It's designed with this JSON interface. So we're working on a Python interface, but essentially right now what you do is describe the model in a model flow description. It takes as input the Parquet files from NVTabular as well as its own custom format. And basically we're accelerating to on GPU by distributing the embeddings across the GPU and then doing both model and data parallelism. So you can do this large scale online training and retraining in a very straightforward and easy way. And it's roughly 7 times faster than sort of out of the box TensorFlow on the GPU. And so there's a significant performance boost when you're training. It makes a huge difference when it comes to these large training jobs, and especially when you start using NVTabular, you end up with these sort of much larger data sets, or you're training more data sets more frequently, and so you need the training to be able to keep up with the ETL. And then the last phase is TensorRT and the Triton inference server. And there we're doing deployment on the GPU. The idea here is SLA requirements. So you specify the limitations of your latency, and then batching is used to optimize the throughput of the model. You can of course tune it towards throughput or tune it towards the latency requirements that you have. It uses an HTTP or a gRPC endpoint, supports a whole range of sort of standard bells and whistles like A/B testing, model ensembling, metrics, and other kind of mature. And it's probably, I would say, it's our most mature component of Merlin. It's the system independent in of itself, and we're just leveraging it for the recommender system space. So,
Awesome.
Yeah, go ahead.
So we will. Do you mind if we can take a couple of questions quickly?
Yeah, absolutely.
Awesome. So my first question will be, from my understanding so far, is the NVTabular. It helps in the data pre-processing part before the modeling aspect. It speeds up the process. I have two questions about that. So number one is, do you expect data to be in a specific format and a specific structure? The second question is, how, like, if do you need the data engineering aspect to be done prior to feeding it to the framework, as in knowing which feature to be included, which feature not to be, or does it do it automatically?
Yeah, so the first question in terms of formats, so like I said, we leverage the Rapids ecosystem, and so their QIO framework supports a wide variety of commonly used formats, from Parquet to CSV to Avro. The Parquet file format is the fastest, and that's sort of what we use for our intermediate format. It's the one that's had the most development done to it. The reason why we like this format is you can also query it in a lot of other methods and languages. So there's some slight restrictions in the sense that you need to do things like specify row group size so that the row groups are a little bit smaller than kind of traditional Parquet files. But just because basically the row group is the minimum amount of data that they can pull onto the GPU, and so if it's the entire file, then the GPU kind of gets overloaded with all the data. But beyond that, there's really it's designed to work with pretty common and standard data sets. Typically, you'd want to be pulling the data, or in our kind of workflow, you'd be pulling or joining your tables in the data lake itself, and pulling out a larger superset of the data. But then there's often feature engineering you want to do on that downstream. You can do the joins in NVTabular and on GPU, and we're working on that component as well. And I think it's becoming more and more feasible to do the whole thing on GPU, and we actually have customers that are looking at, like their data lake is stored in Avro format, and they're looking at targeting those files directly and pulling the data from that directly. And it's much faster to do these on GPU once the files are aligned and it's working. That being said, your data format may be in a different format from what, like if you're on BigQuery, for example, then so the data needs to be exported first in order to be able to be pulled into the NVTabular system. What we do in the NVTabular as well is to prepare the data for model training. As you're doing the feature engineering and pre-processing, we're generally, we can save that out in a Parquet format that's super efficient for loading the data for training, because you're iterating through multiple epochs of training. You want the data to be in the most efficient format.
Okay. So in addition to the model format, I also had that question of what kind of data do you expect? Because, like, for example, when you're looking at the current platform for a commander system, some organizations expect sequence data. Some of them expect the holding matrix or the utility matrix. So what kind of expectation of the data should it have? Should it have the user information, or user information is not required? How do you deal with these different kind of data that each recommender engine deals with different kind of data in a different ways, right?
Yeah, the manipulations you could do to the data are we're currently working on session-based recommender systems and how to format the data for aggregating sessions. Right now, it's more designed around interaction level data, but we have a research project, and we're currently working towards in the next couple of months the session-based style that you're talking about, where where user sessions need to be aggregated together, and you need to make that that as part of a batch the user session stays contiguous. So beyond that, there's not really restrictions on the data formats or the types of data that you want to include, beyond sort of the general concept that it's tabular data. We don't explicitly exclude image data or text data, but generally speaking, we find we're working on those in a pre-embedded format. So if you wanted to data load images and the tabular data at the same time, the images tend to be the bottleneck in terms of the data loading, and so something like Valley can actually do a pretty good job of keeping everything loaded at the same time.
That's awesome. Ali, you want to ask any question?
Yeah, very cool. So we have a couple of questions from our online audience. Somebody asked, how does GPU accelerated data pre-processing work? Does the user need to follow certain frameworks or guidelines and write the pre-processing code differently? In the other word, what exactly is being accelerated on GPU data pre-processing?
Yeah, so we leverage and sit on top of the Dask cuDF library. So cuDF is a data frame library that accelerates data frames on GPU. The API for that is nearly identical to Pandas. It's very, very close. And so if you're used to doing Pandas style data manipulation, you can do that directly in Dask cuDF. The NVTabular API, we'll get into it in this next section, and it's designed to kind of up-level this. So it really, like, we've tried to come up with a higher level abstraction. I'm a student of Jeremy Howard and the Fast AI course, and so in that course, there's design principles around essentially API design and making it as simple as possible for the user. And so what we're trying to do there is up level and provide these higher level abstractions that allow you to really think about, what you want to do instead of how to do it. So we take the all of the challenges of the data frame level, like, okay, how does a normalize happen? How do I get it to happen across all of these columns? How do I scale that across all of the GPUs? We abstract all of that away, and you can just say, I want to normalize my continuous columns in this way. And it'll behind the scenes create a Dask task graph, schedule that on the GPU. The GPU accelerated data frames, if you're not familiar with Rapids, I highly recommend you go check it out. It's amazing what that system can do. Typically speaking, if you have sort of traditional Pandas workflows that you're used to working with, you can get a 10x speed up, and in many cases you can get that just by saying import cuDF as PD, right? So it's the accelerations you can get are quite significant, and it's a really powerful library, and we're essentially leveraging that and providing a higher level API and kind of solving for some of the common recommender system pre-processing and feature engineering steps.
Very cool. I'm also a student of that course. There is a new 2020 version that people check out at fast.ai. So there is another question. So it's more of a business question. Like, are there companies already adapting Merlins as their own recommendation engine? And also, the audience asked that Rapids and Triton, I guess, seems to already be a well-known project from NVIDIA. Is there any special optimization on applied for Merlin as a whole framework, basically?
Yeah, so like I said, Rapids we're building upon, and so we work very closely with the Rapids team and rely on them, and it's a very, very close interaction. We're kind of layering on top of. It's one of the beautiful things I love about NVIDIA, the NVIDIA ecosystem, and working at NVIDIA is there's the hardware, and then the drivers, and then the CUDA layers, and then the libraries built on top of that. And we're several levels of abstraction higher, and I think it provides for both a richer ecosystem and also sort of very, very sophisticated APIs, and it lets you build things more cleanly. Can you remind me of the first question or first part of the question?
Okay, so the first part was about are the companies who are adapting?
Yeah, so we have a number of companies that are using Merlin in production, and we also have, and I think the person asking the question sort of talked to Triton and Rapids as being more mature, and they absolutely are. They've been around for a lot longer than the Merlin. HUGECTR has been around for about 2 years now. on its own, and NVTabular is is in the last 6 months. We've really kind of accelerated its development, I would say. Maybe a year when I was working on it a long time ago, but yeah, it's seeing a lot of there's on the NVTabular side. There's a couple companies that are starting to work with us to deploy it into production. On the whole scale Merlin, or on the HUGECTR, there's a number of companies that are using it in production already. And then Triton is, as you said, a very mature product that lots of companies are using that already. In terms of explicit optimizations for recommender systems, we're working with the team right now to add a bunch of those features and working on scaling embeddings and a number of other challenges that you see for recommender systems in Inference.
Perfect. Thanks.
Great questions.
Thank you. So I don't think there is any other questions from the audience. I think we can continue with the second part.
Great. Okay, well, let's go into some of the details of the three components. So yeah, NVTabular is sort of the team that I've built up. And basically it sort of comes from my history of being a data scientist and trying to develop these models and really finding that building the data sets are the most time-consuming component. And I don't know if you've seen this diagram before of the CPU versus GPU powered workflow that the Rapids team developed, but on the left-hand side, that wasn't far from my day of you start an ETL workflow and then you're kind of waiting for it to get done, and you go and get a coffee and you talk with a coworker about a paper, and you work on another project for a little while, and then you go back and check on the ETL and something wasn't quite right about it and you have to restart it, and really you're only getting maybe 2 or 3 ETL jobs done a day, and you're logging in at night to try and get one overnight, and it's these jobs take a really long time. And when you can accelerate them onto the GPU and get them happening much more quickly, it really lets you kind of focus on building the data set much more. You can get into that flow zone of like, oh, I forgot that feature, I'm going to add it now, and you're not as Josh Patterson, who heads the Rapids team, likes to say, we're helping data scientists kick the coffee addiction, right? You don't have to drink 4 or 5 cups of coffee while you're waiting for your jobs to run. You can actually get down to work. So that's the core motivation behind this. NVTabular is meant to do the sort of the feature transforms and the pre-processing on GPU. I think I mentioned earlier that there's no limit to the dataset size, so you're not bound by GPU or even CPU memory. It's better if you have enough CPU memory to host the dataset or large chunks of the dataset, because the way Dask works, there's sort of when data doesn't fit in GPU memory, it spills to host memory first, and then to disk if there's not enough host. And I think I talked enough about the higher level abstraction, but really. The core idea is describing what you want to do. So you don't have to think about the scaling. You don't have to think about the other components. We support some data loaders for PyTorch, and TensorFlow has recently been developed. So there's DLPack is kind of our mechanism for passing data between the frameworks. It's this methodology where you essentially pass pointers, and depending on the structure of the data, it can be 0 copy if the data is differently structured. And I think in the tensor case, it's slightly differently structured, so you do have to do a copy. But it's instead of copying item by item or batch by batch or whatever else, you're copying like large contiguous blocks of memory. So it makes a huge difference in terms of the performance of the memory transfers. So this is probably the most complicated diagram we're going to see today. And this is just our sort of conceptualization of the recommender system pipeline. So, starting at the top left for training, you've got this data lake, and you're pulling, petabytes of data potentially out of this giant exabyte data lake, and then filtering it down, doing some feature engineering, doing some pre-processing down to, probably terabytes, maybe 100 terabytes, depending on your scale, machine learning ready data sets. You've got the data, you've done the normalization, you've done the categorical representations so that they're encoded, and then you're loading the data into PyTorch or TensorFlow, maybe HUGECTR, and then those model weights, once they're trained, get passed off to the inference server, and you're sort of iterating both on the model tuning and hyperparameters as well as the feature engineering. So you're basically cycling through the building of the data set, and you're cycling through the model and hyperparameter tuning. And essentially, with NVTabular, what we try and do is say, okay, well, let's turn all of these into something that's happening on the GPU efficiently and quickly, and provide a library that makes it easier to do, and then provide a mechanism for exporting these so that you can basically pass the pre-processing config and the feature engineering config from this stage where you're building the data set over onto the inference side. And that's what we're working on right now is basically how to do the same steps from training at inference time. And that sort of allows for production deployment in a much more straightforward fashion. We also have our NVTabular Dataloaders. I'm going to share with you some numbers for those. Like I said, the PyTorch one has been out for a little while. The TensorFlow one is coming out with our 0.2 release, but you can find it on our GitHub repo already if you know where to look. And we're seeing significant speed ups when you load the data in the proper way. It makes a huge difference in terms of performance, and then beyond that, you start to see benefits from things like AMP and using mixed precision. So I talked about the code and sort of the simplicity side. This is NVTabular versus I guess it's a NumPy example. I need to keep updating this slide. The core idea for NVTabular is specifying sets of variables that you want to process in certain ways. So you've got your categorical variables. You generally want to encode them, right? You've got your continuous variables, and you generally want to normalize them and do other things to them. So this is a very simple workflow. This one we took from the DLRM repo. So DLRM is Facebook's deep learning recommender model, and they provided this ETL workflow, and we'll see sort of the performance of it. But the NumPy version that they originally provided was, required an insane server with multiple terabytes of memory, and it still took 5 days to run the ETL. So it's incredibly inefficient and slow, and it was about 1,200 lines of code. It could have been reduced to about 500 if you really cleaned it up. But at a high level, what we're trying to do for NVTabular is provide this mechanism where you can say, these are my categoricals, these are my continuous. This is what I want to do to my categoricals. This is what I want to do to my continuous. The feature engineering side, you can add new categoricals and new continuous variables, and that lets you kind of fill out additional features, and it all gets basically pre-computed into a task graph and applied to a large or applied to on the GPU to optimize. So we've got an upcoming NVTabular version. We basically added support on the multi-GPU side, so you can scale to multi-GPU, and we're now working on multi-nodes. So you can run this, of course, on a single GPU, and we tested it on GPUs with as low as 11 gigs of memory. But the more GPU memory you have, the more optimal it is, which is basically scaling it up in memory gives you more efficiencies. And so the A100s that are coming out are even better for performance in terms of this. And then on the data loader side, we've got PyTorch, TensorFlow, and HUGECTR. And we're working on multi-GPU data loading as well, so you can scale the data loaders or scale the training across multiple GPUs. And then I talked about basically being able to do common operations, and so we're adding things that you commonly do when you're building data sets, like target encoding, difference lag, column similarity, dropping nulls and filtering and those sorts of things. And so there's a full operator set available on our website. You can take a look at that, and our GitHub has everything available there. We'll be releasing at the end of the week, actually, a new version. that you can check that out. I think I explained a little bit about the data loaders, but the core idea behind our data loader is essentially that, like, rather than grabbing items one by one and collating into a batch and pushing it to the device, we're reading large contiguous chunks of data into GPU memory and then shuffling a buffer in memory to create an on GPU buffer, and then iterating over that buffer to create the batches. So you're not doing item level reading of files or memory, which is much faster. You can scale to much larger batch sizes, which is interesting. It's something we're working on now. Is like, how do you train at these huge batch sizes, and can you get similar levels of performance? Because training does scale really quickly as you begin to scale the batch size. And then, the data loading bottlenecks when you're using the data loaders begin to disappear, and you can start applying other things. So this is an example from our TensorFlow data loader. And I'll just step through really quickly, but you can see sort of CPU native data loading. This is the throughput down here. And if you go to GPU on native TensorFlow, you get a performance improvement, but it's really not that significant, especially relative to the cost. You're not optimal yet in terms of performance. And I think this is something that we've commonly seen in industry, and I think sort of where this adage that I've heard regularly from people that that GPUs aren't well suited to recommender systems comes from, is that the data is not being loaded efficiently, and so the GPUs struggle to really leverage all the compute that they have. There's not enough data flowing into the system. And you can see, like, the orange line, which is kind of right underneath the blue line as well, or just slightly above it, is when you try and improve the performance of the GPU, you say, okay, well, maybe what we can do is add mixed precision, and we'll get a better performance out of that. But really, you don't see any significant improvements in performance, because the part of the problem that you're solving for, the training side, is not really being properly leveraged. Conversely, when you switch to our data loaders, you start to see much better throughput. So we're seeing a 4 to 5x improvement over the GPU performance previously. And because the GPU's got good utilization, when you apply mixed precision and add that in, you get even better performance. You get roughly 10x performance over the GPU, 20x over CPU when you're using these data loaders. And there's some proclivities, and we're working on improving the performance beyond this even. But we're working hard to basically figure out the optimal way for loading data onto the GPU. This is one of the most exciting things that I'm sharing today. HUGECTR is our training framework at scale. Again, we're training faster than TensorFlow. It's designed specifically for recommender systems. So we do things like, in recommender systems, there's common kind of layers in the models that we can say, okay, well, when you're feeding data in, you're generally hitting an embedding, and there's some cross layers and there's some downstream layers to that, and we can fuse a lot of those layers together to speed up performance. And then we can also scale the embedding side of things such that that the embeddings are fitting onto the GPU across multiple GPUs if your embedding tables are large like that. And so we support model parallel training and scaling to the embeddings across multiple nodes even. And then there's a mechanism for turning the whole embedding table into a single GPU hash table with dynamic insertion, so you can kind of do online training where you're adding new values to that. And there's a straightforward data pipeline. It uses JSON as the sort of the configuration for it, and we're working on a Python interface as well. And like NVTabular, it's also an open source component. It has asynchronous, multi-threaded data pipeline. So the data reader is doing some of the things that we do in the TensorFlow and PyTorch data loader as well, where the data is getting grabbed sort of asynchronously. There's multi-node all-to-all communication, and so that the data can get efficiently from any GPU to any other GPU when it needs to, and it's both data and model parallel. So there's a very efficient architecture behind this. You can do all the things in HUGECTR that you can do in HUGECTR in TensorFlow or PyTorch. It's a little bit slower there, but it's a lot more complex to write. And I think both NVTabular and HUGECTR are designed to try and make some of these things a little bit easier. We're working with the frameworks teams, both TensorFlow and PyTorch, to integrate some of these components into TensorFlow and PyTorch, and if that's your native training library, we're working to add those as well. This is a high level sort of the multi-node model parallel. The core idea, you're just spreading the embeddings across the different GPUs and the different nodes, and then each GPU also has the entirety of the dense model, and we use a parameter server to kind of align the models there, and then support a bunch of different training mechanisms. And some of the operations happen kind of on the GPU after you grab the embedding, before you pass it on. So if you're doing something from one part of or from multiple memory slots on the GPU, the operators like the additions, the averaging, the concats, whatever can be done to that slot will be done to minimize the amount of transfer that happens. So there's sort of a mechanism for reducing the amount of data transfer that's going to happen. And then the final stage is Triton Inference Server. As I've said, it's sort of our more mature. You're potentially already using it for doing images or for doing text, or BERT or some of these other models. It supports multiple frameworks. You can run multiple models simultaneously on a single GPU, and that's one of the ways it's made more efficient. Is you can actually have on a single GPU, many models sitting and waiting and ready to be run, and you can scale across multiple GPUs and do distributed inferencing across sort of all system GPUs. It's got metrics and monitoring and a C++ library for direct integration if you want to just bake it right into your app. So it's much more full featured. The team's been working on this for a number of years now, and it's sort of a much more mature product. At a high level, it's sort of designed to maximize your real-time inference performance. So you can deploy to multiple different GPU instances. Here it's deploying to T4s and V100s and P4s. It does the orchestration, it does auto scaling with latency and health metric, or integrates with orchestration systems. It's got like I said, latency and health metrics. So you can really build this into a production system quite easily. And it's also open source, and there's a lot of customization you can do. And if the customization doesn't sort of fit your needs, you can build on top of it to kind of provide the final stages. We've got a number of different models examples on the recommender system side on Triton. So you've got DLRM and wide and deep cross networks. In each of those cases, we're working on optimizing them in HUGECTR, in TensorFlow, and in PyTorch. And then from there's a number of different options for feeding intermediate files. But Triton Inference Server accepts all of those models and allows you to deploy onto the P4, the V100, the T4, and now the A100 with MEG, which allows you to really scale. So it's a very full-featured system. So I think we're getting close to time here. I did want to have time to go through an example, so I'm gonna skip ahead a little bit, but maybe I'll just cover the latency very quickly. So there's a very fast real-time response from these machines. You can get a much lower latency thresholds with GPUs than with CPUs. The total cost is generally speaking lower as well, especially as you begin to scale to higher batch sizes. And so depending on your recommendation use case, if you're comparing thousands of options, GPUs are definitely a great choice. There's a really good paper out from Facebook and Stanford that talk about kind of the scale at which GPUs begin to become appropriate, and we're working on kind of updating that to include the production scale of GPUs as well, because they show that the performance is on GPU is good above a certain batch size, but the GPUs they test on are actually kind of more commodity 1080 Ti's and not production scale servers that are available. So I talked earlier about the DLRM model. It's tested on the Criteo 1 terabyte ads data set. So Criteo is an advertising company. They provided this as part of a Kaggle competition originally, and then expanded it to a full terabyte, well, at 1.3 terabytes uncompressed. It's 26 features with very, very high cardinality on about 5 or 6 of the features. The original NumPy ETL and CPU code that they provided, or NumPy ETL code, took about 5.5 days, and then training took about another 2 days. So you're looking at, you know, a full week if you're operating fully on CPU. And this just highlights the NVTabular story, or why it's important, in the sense that, you know, like, if you accelerate the training and run that on GPU, that's not enough if you're you know, if your ETL is really poorly performing. I've had to blow this up because, as you can see, the final stages of this don't exist on that chart. So I'm going to scale that part of it up. So we have a team that's dedicated to Spark at NVIDIA, several teams actually, but one of them was kind enough to take this and rewrite it and optimize it for CPU, and really came up with an optimized version. We ran this across a GPU cluster that essentially is about 2x the cost of a V100 if you're going to run it in the cloud. So these two you can compare it at roughly 2x the cost. And the 4-hour timing here is 3 hours of training, or sorry, 3 hours of ETL, and then another hour of training using sort of a standard PyTorch on a V100. And we worked to accelerate that both in NVTabular, and then on there's sort of been some updates that have been made to PyTorch to accelerate the DLRM model. It was part of the ML-Perf benchmark, which is a benchmark for improving performance. And so there, we were able to get things down to 51 minutes on a single GPU. So you're getting to the point where, that hour-long cycle to create a new data set and train it is actually kind of in the realm of, you can do a bunch of those cycles a day. You can maybe have multiple machines that you're running this on, so you can try, different variations, different feature engineering stages, and iterate really quickly. And the nice thing that I really like about this is, is on a DGX, which is a system with 8 V100s here, you can scale that even further. So the training can get down to about 3 minutes, and ETL about the same. And so, we've made some major strides and improvements to HUGECTR and to NVTabular to scale it to multiple GPUs. And you can imagine, like, this is 1.3 terabytes of data being read in from Parquet files on the hard drive. So we're reading this in this case from NVMe drives, into GPU memory, transforming the data, preparing it for model training by doing categorical encoding, doing normalization of the continuous variables, and some log transforms and a few other things, and then passing that data over to HUGECTR, or saving that data out into Parquet, passing that data over to HUGECTR, and then HUGECTR is doing the training in about 2.5 to 3 minutes as well, again, across an 8 GPU system. And so, it's a much larger system, but you're able to scale it to, pretty much linearly, which means that, the cost is the same between the two. You're just getting your results much more quickly. This is maybe a bit confusing, but I'll try and talk you through the high level. So this is what the ETL process looks like. This is in real time. The center is the task scheduler, and it's sending sort of tasks to each of the workers, and then the red lines are the workers communicating with each other. And you can see, there's lots of all-to-all. The GPU utilization is very good, and you're seeing, basically the performance of the system in real time in terms of its ability to basically perform these tasks. And so, it's the idea that you can take a terabyte of data and process it and get a machine learning model ready in literally a few minutes, and we're watching that happen in real time is a pretty awesome one for me. It's why I'm excited about this, and why I got into this in the first place is, if you can do that sort of that work that used to take a day in a few minutes, then suddenly you're able to iterate much more quickly. You're able to come up with better models, and your focus can be on the modeling side of things instead of having to wait for the data to come to you. So that's what I have for you today. These are our GitHub repos. So there's the NVTabular repo, the HUGECTR repo, and the Triton Inference Server repo. Thank you so much for the opportunity to talk. Really appreciate it.
Yeah, thanks, Evan. I guess we still have a little bit of time for a couple of questions. Omar, do you have anything that you want to ask first?
Yeah, I got a couple of ones. So like from my understanding, the HUGECTR is responsible for the training aspect, but my question would be, does it take any kind of model? Like if I decided that my data requires a specific kind of form, like model to it, does it take any kind of model, or it has model-specific requirements?
So there's some limitations in terms of what it does. Like I said, it's recommender system specific. So yeah, we're not trying to build PyTorch or TensorFlow again. They've done a great job of building those. But for the particular types of model architectures, I would say it depends. Most model architectures it'll cover, and we're working on adding additional features. So if there was something that you wanted to see that you didn't see there, we'd be very happy to work with you to add it, and you can make a request on the GitHub page. If it's something that that you didn't want to share publicly and wanted to make the request in private, we could talk about that too. And at an extreme, if you wanted to develop it on your own, the project is open source, and you can easily add your own kind of layer or module if you're willing to get down to the HUGECTR is kind of a lower level C++ library, so it's, you need to know your CUDA programming to be able to really dig in and make it work, but you can definitely optimize and come up with your own kind of libraries and model architectures in that way. It covers a broad range of the sort of the standard recommender system architectures.
So what you guys built is fantastic, like starting from NVTabular, where you're preparing and massaging the data, up until the HUGECTR, which is the modeling, and then the inference part. But let's say one of these components I decide to actually do it on my own. Does it support that or no?
Yeah. So the Merlin framework as a whole is just sort of us making these components work really well together. But like I said, NVTabular has the data loaders for PyTorch and TensorFlow, and so it's designed to work within that ecosystem. HUGECTR has a number of different file formats it takes in, including kind of its own custom binary format. And Triton Inference Server is very flexible. It can take input from from the widest range because it's the most mature. But you can pick and choose each of these components. In fact, we have customers that are running just HUGECTR in production. We have customers running just NVTabular, and lots running Triton. So if you want to pick and choose to meet your requirements, say if you're a TensorFlow shop and you've got an inference serving pipeline already working, we can work with you to get NVTabular and the data loaders for TensorFlow working with that, and then we're working on production deployment options for TensorFlow serving to integrate the NVTabular operations into the task graph there. And the idea is that we'll be fully interoperable with the entire ecosystem. We're just putting an extra effort in because we know how much challenge it can be to get these pieces to work together. We're trying to make sure that there's an easy example of it all working together in the Merlin umbrella.
Awesome. Ali, do I have time for one more question, or?
I also have two questions on my plate. Let me ask something. We can ask the last one, hopefully. So as you mentioned, even the most interesting part of this framework is actually where you have like the distributed manner of loading data as well as doing the training. I'm just wondering, like, what is in the underlying layer of all of this distributed manner? Is it like the CUDA and CUDA-NAND, or for data loading you mentioned DASC is what used in the lower layer?
So on the data loading side, we use a library called QIO, which is part of the Rapids library. And that's what sort of all of the Rapids libraries are using for loading the data. If you're pulling the data from a file, so Parquet or CSV, those all basically go direct to GPU memory using the QIO library. So it's the Parquet data is even, I believe, getting decompressed on the GPU as you pass the data over.
Right. And for the training side, like the HUGECTR.
Yeah, for the training side, so HUGECTR is essentially there's an asynchronous cert system running in the background, preparing the batches for the next training iteration, and it uses uses that sort of asynchronous system to make sure that there's always a batch waiting and ready to go. And then the training loop itself is it's using, so there's two versions. There's the binary version, which is sort of uses I'm not sure what framework they're using for transferring the data over. It might be Nickel. And then the cuIO is being used for the Parquet side of things.
Yeah, thanks. One of our audiences asked, how well does the NVTabular scale for computation on graph networks like GNN and GCN?
That's a great question. We're actually literally looking into that. The challenge with graphs is, similar to sequence-based, you need to make sure that certain parts of the data are correlated together. And so, the pre-processing of that data we can absolutely do. In the data loading side of things, we're working to try and figure out ways to, intelligently load the data and aggregate the data so that you can do things like a random walk within a certain range on subsets of the data, so that you're not having to hold, like the challenge you run into with some of these is if it's not framed properly, you have to hold the entirety of the data in memory, and that's where where things become a much bigger problem. But I love that somebody saw that vision, because that's exactly the sort of one of the next steps that we're looking into is all of these principles for tabular apply to graph and GCN, and we're looking at there's the first experimentation that we're starting to do is with DGL, the Deep Graph Library that's open sourced by Amazon, I think, and they have a system there. It's a bit more complex because it's multi. It's like MXNet and PyTorch and TensorFlow, and the different backends are a little bit different, and so we're working to figure that out. But once we get things really working for tabular data and for this space, we should be good to go.
Awesome. We have 1 minute.
I'll do it very quickly. So dealing with most of the businesses right now and dealing with most of the clients, I assume they have some sort of business rules that needs to be applied on top of their modeling. Is there any part that deals with this at like the platform?
Yeah, so the missing piece of the puzzle and I think in the initial diagram we cover it, but we haven't sort of covered it in the Merlin sense yet, is candidate generation. Like what we're looking at here from the modeling and training side of things is the downstream, the deep learning models. Candidate generation is on our roadmap for next year, and something we're planning on looking at, and that's sort of where I generally see business models applied, or business logic applied, is you use the candidate generation to make sure that the input to this model is all relevant. And then kind of the downstream model doesn't have to think about it. So that's where we're thinking about it and trying to figure out, like, okay, can we put like there are on GPU databases and GPU memory databases that are very efficient and fast in memory, and can we do the sort of the work there to make that efficient?
Okay, so you're thinking of upstream more than downstream at this point.
Yeah.
Okay, makes sense. Okay, awesome. Thank you.
Yeah, awesome. Is there any last words, Evan, you want to mention?
No, just thanks very much for the opportunity to talk. Feel free to reach out on any of our GitHubs. You can leave an issue if there's something you find that's not working. Give it a try. We're going to be launching NVTabular at the end of the week here, and so there should be new versions. And there's a lot of flux in our repo right now, but we'd love to hear from you if you've got an issue or an idea. Feel free to reach out by email or Twitter as well. If you want to communicate more in person or privately. And yeah, we're looking for customers who are interested in using these libraries. ideally customers that have deep learning recommender teams in place and understand the problem. And so I think we're really building this up. We're hoping to get to the point where this becomes a more straightforward enterprise solution where you can kind of feed the data and it's a push button system where it solves a lot of the problems along the way for you, and the data scientists can focus on the feature engineering and the modeling and don't have to worry about production deployment or those sorts of things. But that's a little ways down the road in our roadmap. So.
Awesome. So at the end, I would like to thank our great speaker, Evan, and the NVIDIA team, especially the team in Canada, for collaborating with us to do a series of great talk around their open source frameworks and the tools they have developed. I would also like to thank Omar for doing the facilitation of the talk, and our stream committee team and the team of stream owners at ACE for helping us and promoting the talks. If there is nothing else, we would like to close the live stream.